We have discussed in very detail the problem of Born approximation to discuss a scattering theory. Now, after knowing about the Born approximation, today we are going to see a very good example to illustrate the application of Born approximation. In fact, this is regarding the atomic scattering of electrons. In fact, when this question will be asked in your examination, it is possible that you have to discuss a scattering by a spherically symmetric potential. So you should note here that when a question will be asked to discuss the scattering by a spherically symmetric potential, you may write your answer in terms of atomic scattering of electrons. It means a scattering of electrons by atoms, when atoms are taken as target. Okay? Because to a good approximation, the scattering of fast electrons by an atom of, let us say, atomic number Z can be represented as the scattering in a spherically symmetric potential. So both of the headings I have actually written here, and question may be asked in terms of either discuss the atomic scattering of electrons or discuss the scattering of scattering by a spherically symmetric potential. Okay. Actually, this is a very important example, and you will see that such a question is generally asked in your examination of M.Sc level. So now, first of all, let us see, if we consider that an atom behaves just as a spherically symmetric potential, what will be the potential created by this system at a point of observation? Here I have shown that this P is the point of observation where the potential will be observed, and O is an arbitrary origin. And relative to O, the position vector of this point P is R, and here actually there is the source of potential, and I have shown an elementary volume of this source of potential, which is d tau dashed. Okay? And the position vector of this element with respect to this origin has been taken as r dashed. So relative to this elementary source, you can see the position vector of the point of observation P will be r minus r dashed. R minus r dashed. This is the position vector. Okay. So in fact, if you want to define the potential due to such a spherically symmetric source at this point P, that will be given by V of R equal to minus 1 over 4 pi epsilon naught ZE square over R plus 1 over 4 pi epsilon naught ZE square and integral over rho of R dash divided by modulus of R minus R dash d tau dashed. Actually, this first term in fact represents the potential just in this manner. If there is a charge plus Ze, which is actually the nuclear charge, and here is an electron, and both are separated by distance r, then the potential means potential energy. So potential energy of this system will be then what? This will be minus 1 over 4 pi epsilon naught ZE square. This will be the potential energy. But here, except this origin, we have shifted the origin to the position r dashed and considered here the source, and then we consider that the electron cloud is actually distributed in this atom, and in this condition we define an elementary volume. Okay, and this is actually the charge of the unit volume, and when you will multiply by this d tau dash, that will be the elementary charge dq. Okay, elementary charge dq. So this is the potential or potential energy at point P. Okay, I have written here, you can see R is the position vector of the scattered electron, and rho of R dash, this is charge density due to the atomic electrons at position R dash. Okay. Now after knowing this expression for the potential, we want to express this potential field in terms of the total charge density. When you talk about the total charge density, that means the charge density of nuclear plus electronic charge. Okay? And if you denote that charge density by the symbol rho t, then this rho t, actually you will see later on, this is given as delta of R dashed minus rho of R dashed. Actually here rho of R dashed, this is actually the nuclear charge density, because here the charge is distributed in continuous manner, and actually this is Dirac delta function, and you know this Dirac delta function defines the charge density due to the discrete charge distribution. So we will see later on that this total charge density, which is due to the nuclear and electronic charge, that is given by delta R dash minus rho of R dash. Here delta R dash, you know, this is the Dirac delta function centered at R equal to 0. Okay. Now, in terms of this rho t, that is total charge density, the potential function V of R may be given as minus Ze square over 4 pi epsilon naught integral rho t of R dash divided by R mod of R minus R dash d tau dash. Okay. Now, as our aim is to find the scattering cross section, and you know that the scattering cross section, that is differential scattering cross section, is simply the square of the modulus of a scattering amplitude. Okay. So first of all, we will have to find the value of the scattering amplitude for getting the scattering cross section. Okay. And as we are going to apply Born approximation to discuss this problem, so you have to remember what you have learned in my previous video. You have seen that the scattering amplitude in accordance with Born approximation is given by this expression defined in equation 3. If you denote the scattering amplitude at point R by the symbol f of k comma k dash, here actually k is the wave vector for the incident wave, okay, or incident particle you can say, and k dash is the wave vector of the scattered beam of particles, here a scattered beam of electrons. Okay, and this is actually equivalent to f of theta comma phi. This is called a scattering amplitude, and you have learnt in the lecture on Born approximation that this is given by minus m over 2 pi h bar square integral of e to the power I kappa dot r times v of r d tau. Actually here, what is this kappa? In fact, if you consider, see this figure, that this k is the wave vector of the incident particle, and k dashed is the wave vector of the scattered beam, then this kappa is equal to k minus k dashed. Okay, k minus k dashed. So this kappa, which has been written here, that is actually the measure of k minus k dashed, where k, represents the wave vector of the incident beam, and k dashed is the wave vector of the scattered beam. Okay. So now let us substitute the value of V of r which has been defined in equation 2 in this equation 3 for getting the value of a scattering amplitude. Okay. So you can see the scattering amplitude after the use of equation 2 in 3 will be given as f of k comma k prime equal to plus ze square over 4 pi epsilon naught times m over 2 pi h bar square and double integral of rho t r dashed over mod of r minus r dashed e to the power I kappa dot r d tau dashed d tau. Actually here this V of r present in this equation 3 has been replaced by the value of V of r defined in equation 2. Okay. So after substituting that value of V of r, we get this result. Now since here V of r the expression for V of r is negative and that for f of theta phi or f of k comma k, that is also negative. So this minus times minus will become plus. Okay. Now for getting the value of this integral, first of all we will cast this expression in a suitable form so that we can evaluate this integral. And for this, let us see, I have done a simple algebra here. In fact, in our original equation you can see here the exponential factor is I e to the power I kappa dot r. But you can see I have written here an extra exponential factor e to the power I kappa dot r dashed. Okay. Since it is an extra factor which was not originally present in our expression, so you must divide by the same factor so that the result will remain same. In other words, we can say that if we will multiply this expression by e to the power I kappa dot r dashed times e to the power minus I kappa dot r dashed, then the result will remain unaffected because this product will be equal to 1. Actually, that algebra has been used here. You can see inside this square bracket I have written integral of e to the power I kappa dot r minus r dashed. Okay. So this e to the power I kappa dot r dash times e to the power minus I kappa dot r dash, that will be equal to 1. And so our result remains same. Okay. In fact, the integral inside this square bracket, this integral within the square bracket may be evaluated by taking the point r dashed as origin in the integration over r. Actually, in that condition, we know integral of e to the power I kappa dot r over r d tau, this equals 4 pi over kappa square. You should remember it. I have not evaluated this integral, but you should remember it. So using this result defined in equation 5, you can write 4 pi over kappa square instead of the integral inside this square bracket. Okay. So after making the use of this equation 5 in 4, our result becomes f of k comma k dash equal to ze square over 4 pi epsilon naught times m over 2 pi h bar square and integral rho t of r dashed times e to the power I kappa dot r dashed times 4 pi over kappa square d tau dashed. Okay. But as I have told you earlier, that the total charge density, which is charge density due to the nuclear charge and the electronic charge, that is defined by delta of r dash minus rho of r dash. Actually here, this delta of r dash is what? Definitely you have an idea of it. This is called Kronecker delta. Okay? This is Kronecker delta. Okay? Now we can replace this rho t of r dash by this expression. And so the expression for the scattering amplitude f of k comma k dash, this becomes Ze square over epsilon naught. Actually here, when you will bring this 4 pi over kappa square factor outside of this integral, this 4 pi present here in denominator will cancel out. Okay? And that's why our result becomes Ze square over epsilon naught times m over 2 pi h bar square times kappa square. An integral of delta r dash minus rho of r dash times e to the power I kappa dot r dash d dot dash. Okay. Now we will try to find the value of this integral. You can see that this expression can be written as Ze square over 2 pi epsilon naught times m over h bar square kappa square times integral of delta of r dash times e to the power kappa dot r dash d dot dash and minus integral rho of r dash e to the power I kappa dot r dash d dot dash. Okay. In fact, this first integral inside the square bracket, this equal to 1. This is just the property of your delta function. And we consider that this second integral, which will be a function of kappa, that is equal to f of kappa. We consider it. In fact, this quantity is known as atomic scattering factor. If you have not an idea of atomic scattering factor, you can watch my video on atomic scattering factor, a complete video on it in the playlist of my channel named Condensed Matter Physics. You will see there a complete video on this atomic scattering factor. Okay? So this integral of rho r dash e to the power I kappa dot r dash d dot dash, this is f of kappa, which is called atomic scattering factor. So in equation 7, instead of this first integral inside the square bracket, I have written 1, and instead of the second integral, I have written f of kappa, which is atomic scattering factor. Okay. Now, let us see. You have seen that this k is what? This is the wave vector of the incident beam or the projectile. Okay. And k dash is the wave vector of a scattered beam. And if you consider that the beam of the particle gets scattered by angle theta, which will be called actually the angle of a scattering, then as kappa is equal to k minus k dashed, okay, k minus k dashed. So modulus of kappa, this will be mod of k minus k dashed. But as you know, the magnitude of vector k and vector k dashed are equal. And when you find the modulus of vector a minus b, and if the magnitude of vector a and b are equal, and theta is angle between them, then simply the mod of a minus b is equal to 2a sine theta by 2. Okay, I hope you have an idea of this formula. So using that formula of vector addition, you can write that this kappa is equal to 2k times sine theta by 2. Okay, and therefore what will be the value of this factor h bar square kappa square? H bar square kappa square, this will be equal to what? This is h bar square is at h, and when you will take kappa square, that will be 4 times k square times sine square theta by 2. But as you know that momentum of the particle p, this is given by h bar times k. Okay, and therefore p square is equal to h bar square k square. But this momentum p square, what is this? This is equal to 2me. Okay, where E is the kinetic energy, or you can say total energy, potential energy is 0. So instead of this h bar square k square, this is we can write 2me. Okay, so this h bar square times k square has been replaced by 2me, you can see it here, and that's why this h bar square kappa square is equal to 8me times sine square theta by 2. Now let us use this value of h bar square kappa square in this equation 7, okay, for getting the value of the scattering amplitude, which is denoted by the symbol f of k comma k dashed, or f of theta comma phi. So you can see that f of k comma k dashed, which is a scattering amplitude, that will be given by Ze square over 16 pi epsilon naught e sine square theta by 2 times 1 minus f of kappa. 1 minus f of kappa. Now actually we are talking about the atom, okay, as a target, and you know the atom may be in its ground state or in its any excited state. Generally the atoms are found in ground state. So if you consider that our system, that is the scattering center, which is actually the atom here, that is in ground state, okay. In that condition, the particle density or the charge density inside that atom will be spherically symmetric. Okay? And in this condition, you can use the result of the hydrogen atom for getting the value of charge density. Okay? So if you consider that the charge distribution of an atom is spherically symmetric, then in accordance with Bohr's theory of hydrogen atom, rho of r dash is given by this result. This is 1 over square root of pi times a cube e to the power minus r dash square over a square. Here actually this a represents the atomic radius. A is the atomic radius. And r dash is the distance of the point from the origin where you have to find this density. Okay? And actually in this condition, when you will take rho of r dash equal to this much, and you will substitute this value of rho of r in this expression defining this atomic scattering factor at the place of rho of r dash, then after evaluating that integral, it is found that f of kappa is equal to e to the power minus kappa a whole square over 4. I have not actually evaluated that integral, you should remember it, because that will be a lengthy process, but for dealing the scattering problem, we have to remember something. Okay, so you remember it. Now we have obtained the value of this f of kappa, and you can put this value of f of kappa here. But before that, let us see if the atomic scattering factor, you know what actually this atomic scattering factor represents? In fact, this atomic scattering factor represents the shielding effect of the atomic electron upon the nuclear charge. It means the electrons distributed around the nucleus acts like a screen. It reduces the effect of the nuclear charge. So it is called shielding effect. Okay? Now if the scattering angle theta is large, it means the shielding effect is negligible. Larger value of scattering angle represent the ineffectiveness of the shielding effect. Okay? So in this limiting condition, when you consider larger value of a scattering angle, then the effect of the shielding of electron on the nuclear charge may be neglected. And so that the parameter f of k, which is actually the measure of shielding effect, that will tend toward 0. So in this limiting condition, when we talk about the larger angle of scattering, this f of k may be taken as almost equal to 0. And so the scattering amplitude f of theta comma phi or f of k comma k dash, that will be simply this much. This is a very important result. But this is just the result. This result is of a special case when you talk about the negligible shielding effect of the atomic electrons on the nuclear charge when theta is large. Okay. Now, after getting the value of this scattering amplitude, you can easily find the scattering cross section or the differential scattering cross section. You know, this differential scattering cross section sigma of theta phi, this is simply the square of modulus of the scattering amplitude. So when you will square this equation 10, you will get this differential scattering cross section in this limiting condition. Okay? And this is actually the expression which I have defined in equation 11. In fact, you have definitely studied the Rutherford scattering in classical mechanics. If you have not studied it, I will suggest you there is a complete video on Rutherford scattering in my channel in the playlist of classical mechanics in the chapter central motion in central force field, where you will get a detailed discussion of Rutherford scattering. And when you will watch that, you will simply find that this result for the scattering cross section is nothing. This is simply the classical Rutherford formula for scattering by a nucleus of charge Ze. Okay? So in this way we can find the differential scattering cross section of the due to the scattering by spherically symmetric potential by using the Born approximation. Okay, and I hope you have definitely understand each and every step clearly. Okay, thank you very much.